Hello, and welcome to the AIM webinar series. My name is Jane Gaston, and I serve AIM Inc. as their Member Relations Coordinator. AIM, the Association for Automatic Identification and Mobility, is the premier source of industry support for the automatic identification market. For more than 40 years, companies have joined AIM Inc. to lead growth of our industry. AIM serves as a hub for quality resources covering all types of barcode, RFID, and mobile computing information. We also serve as an incubator for new auto ID innovations that grow the market. AIM delivers trusted resources that connect you with the new customers and business partners. I would like to direct your attention to your monitor to review a few housekeeping items before we begin our presentation. Attendee phone lines will be muted during the webinar presentation. Please do not use the, quote, raise hand option during the webinar presentation. All questions may be submitted only to AIM Inc., the host, throughout the webinar via the chat option located at the top of your screen on a drop-down menu. Please send questions to AIM Inc. as they occur to you. Questions will be answered during the Q&A session at the end of the presentation. Without further ado, AIM would like to thank SecureRF for their support of today's event. Our speaker for today's webinar is Louis Parks, President and CEO of SecureRF. He will be conducting the second presentation in our AIM webinar series, Securing the Internet of Things, Challenges and Opportunities. Please welcome me in joining Louis Parks.
I thought as a bit of an introduction to this webinar, a little bit of background on our company and what we do, and specifically we focus on securing IoT or Internet of Things devices. We tend to focus on the smallest of Internet of Things devices, and in the presentation we're going to talk about what those things or what Internet of Things devices are. When we talk about doing security, it means more than encryption. Again, as we'll learn in the presentation, we focus primarily on authentication and various types of confidentiality and integrity when it comes to security. Specifically, we develop applications for securing supply chains and anti-counterfeiting, as well as providing security solutions to semiconductor companies and others involved in near-field communications, RFID, and sensors. We're active in a variety of standard groups, including ISO, and also industry groups, which is important and I think will be part of the presentation towards the end for those interested in continuing to pursue this topic of interest. And finally, we've been recognized in the industry. I'm very proud for everybody who works with me to enable this, most recently by Gartner in the IoT for our mobility and security solutions, and also last year as part of one of the top companies focused on Internet of Things by Forbes magazine. So I think a good place to start, because we don't want to boil the ocean, is what is the IoT? I think most people on the phone or on this webinar have some knowledge, or in some cases have a lot of knowledge of what the Internet of Things are. I was pretty amused that about 8-9 months ago I was at a standards meeting in London with 50+ experts, and the initial order of business was to provide a definition to the Internet of Things. That part of the meeting went on for 4 hours before we gave up, the collective we. So I think it's important for purposes of today's discussion that I do provide a definition of what the Internet of Things are, just to lay some groundwork for purposes of discussing security. So with that in mind, I actually have taken from one of the standards groups this chart. And we don't have to go over the whole chart. All I want to point out is in the upper left-hand side, it says person, objects, location. So things can be many things. Many of us are sitting here going, well, my smartphone is a thing on the internet, or my laptop. It can be an object. It could be a building. It could be something innate. And for some of the technical people on this call, a quick distinction I think that should be pointed out is that not everything on the internet has an IP address. And for those non-technical people, this is the series of numbers usually used to give a specific technical location for the purposes of identifying and communicating yourself on the internet. And not everything gets an IP address that may in fact end up on the internet. So a summary definition here might be an object or a person that gets a digital identity that can be used on the internet, as a very, very simple way of boiling it down. So very, very technical definition, very, very technical way of looking at the Internet of Things. Maybe an easier way to look at it is, what are things that are connecting to the Internet that are considered part of the Internet of Things? And as you can see here in this very, very small representation of these things, stuff you already know: a smartphone, a medical device, a fitness element, your home. And certainly we've heard a lot about everything from refrigerators to cars. So there are things that are small, there are things that are large, and growing in terms of excuse me, what those things are. So how big is this world, or why do we care about the Internet of Things, or why do you hear so much about it? Well, I have here one view of the Internet of Things, which simply shows things or devices against people, and that in fact there are 3 times more things on the Internet than there are people, and it's going to grow even bigger. This happens to be an older slide, and this slide I would suggest came out, or this view of the world, that there'll be 50 billion things connected to the Internet by 2020, less than 5 years away. Was, at the point where everybody was excited, this new category, and anybody who's worked in technology knows that we all love the introduction of a new category, which usually means a new market. Having said that, I brought up this, what I'm going to call the adjusted view. It's still big, but this is a more recent view which has downgraded us to only 30 billion objects may be connected. As you can see, the source for this is actually a variety of research entities and consulting firms and what have you. 30 billion, I would suggest, is still big. And to some of you on this call who may work in the areas of RFID or NFC, the small chips and or communication technologies now being used to address logistics, supply chains, etc., those things alone run into the billions. So in deference to my associates at RAIN, which is an RFID organization, and others, this number technically is probably much, much bigger, using a broader definition of a digital entity on the Internet. In the end, even with the lower definition, we're talking about an opportunity or a network or a marketplace where 5,708 plus devices are joining every minute of every day. So it's probably, something that is of interest, of importance, or concern, depending on, where you come from or your industry. As a matter of fact, humorously, what does it mean when devices join the Internet? And I have many of these. I pulled this one out today. When things join the Internet, in a simple cartoon that says, "Bad news, the scale is threatening to cut off our access to the fridge." And certainly now you can go to your local technology shop and buy a scale that connects via Wi-Fi, and it is a thing on the Internet. And whether you're using a connected fridge or just reading about how they're being hacked, that's all there. So this is cute and true, possibly. And I'll be looking into it after this call. So, we've defined the Internet of Things, I think, for the purposes of today's discussions, and that is the objects or devices being given a digital identity. But today's topic is about security and securing those things, and if we can. So having said that, I think probably what we want to spend a bit of time now is discussing what is security. Oftentimes when I meet people and I tell them that, I have a company that I work with and we do security on the Internet of Things, they say, oh, you encrypt stuff and, of course, decrypt. And I go, well, that's one of the things we do. But security really, as defined here, is a collection of mechanisms and procedures and controls that can be implemented to reduce the risk of specific threats. And I'm not, again, for the purposes of today's discussions, going to get into man-in-the-middle attacks, cloning, spoofing, all the things that can happen and we hear about on the Internet and why we all have different types of technologies to protect our networks and our PCs and maybe even our mobile phones, but rather to keep us sort of on track, I'm simply going to talk about some of the mechanisms that we use or that are part of the world of security and how they might apply or are applying to the Internet of Things. So, for example, authentication. You get that email and it says it's Citibank and they'd like some information about your bank account. How do you really know that it's Citibank? Data integrity. Okay, so I've sent a message to somebody and said, please send me $100. I'm stuck in London. How do they know I asked for $100 and not $10? And somebody's going to skim $90 off the top, especially if they're asking for it in Bitcoin. Confidentiality. I send somebody a message. I don't want anybody else to see the message. And again, that could be a case where the magic word encryption or decryption comes up or ciphering text. And non-repudiation. How do I prove that I sent you the message? How do you prove you received the message? So these are all typical things you may have heard in the context of email or using technology, but they certainly apply to the devices that we use today and the things that we might want to consider when using things on the Internet. So what I'd like to do now actually is take the next 10 minutes or so of this presentation and just give everybody a bit of a security primer. We won't quite be ready to put up the walls and protect our networks everywhere, but I think it's important to understand some basic concepts and methods about security so that when we talk about how can you secure the Internet of Things, you'll have a working understanding and perhaps, if nothing else, give you a foundation to ask better questions. So in the security primer here, this chart really shows in the broadest context the world of security or cryptography as we know it today. Really, it represents the two general areas. On the left-hand side, something called private key systems, or sometimes called secret key systems, or for those of you technical, symmetric. Been around for thousands of years. Caesar used to send his messages to his generals in the battlefields, encrypted or hidden using private key systems, shifting the letters 3 to the right, the general shifts them 3 to the left, reads the message. On the right-hand side are something called public key systems, and we're going to get into a little bit more about what these things are, but public key systems have technically been around only about 40 years. This is a relatively new field, but a very, very important field as we'll discuss, and something that has really enabled us to operate on the Internet as we know it today. So I'd like to just go through briefly, give everybody a foundational understanding in a general sense of what private key is and what public key is, and then we'll look at the Internet of Things again and see how they may apply. So, public key and private key. As I've already given a brief definition, private key is where I have a shared secret and somebody else has a shared secret, and we can use that shared secret to communicate and do some other things. If you have a Wi-Fi router at your office or home, you're using a private key system. The router has a secret, and if you have the same secret, the two of you, your laptop, PC, smartphone, tablet, can talk to the router. So that's your shared secret. Public key is a little trickier, and I'm going to get into some specific examples, very simple examples, but public key is a situation where each person has a private key and a public key, mathematically connected. And the public key can be shared with anyone. And there are two methods, and rather than define it a little further, I'm actually going to use the next few slides to give you very specific examples so you understand how it works. Public key is sometimes called asymmetric, because different keys are used, because it gets a little confusing to see that, gee, there are private keys in a public key system, and a public key system also has public keys. So there are some other terms, but I think the next few charts will help disentangle this verbiage or this wording. So let's just use a couple of charts to explain what and how these security things work. As I've already mentioned, what private key is, and in classic cryptography, we always have Alice and Bob who want to talk or communicate or authenticate each other. So in this picture, we have Alice in the upper left, Bob in the lower right. And you can see that Alice has a shared key. We don't know what it is. Nobody here knows what it is. But she uses it in an algorithm or a method to encrypt a message, to create a ciphertext. And that could be as simple as something as she has the number 20, none of us know it, and she's moved all the letters of the alphabet 20 to the right. Somewhat simple, likely easy to break. They get much, much more complicated, and there's some very good ones. When Bob receives the message, he has the secret key, the number 20, and can put it in the protocol and decipher it, and goes back to what's called the plain text or the message. Very, very simple system. And again, used on our Wi-Fi routers, used everywhere. There are some issues with private key, in particular something called the key management challenge, and that is, how do I tell Bob what key I'm going to use if he was sitting on this phone and everybody else here was listening in? Or if you're on another public airwave called the Internet, and I now want to send my credit card to Amazon, and I want to encrypt it, how do I tell Amazon what key I'm using? And do that so nobody else on the Internet knows or hears or sees it. That is difficult to do. It's, in fact, technically you can't use asymmetric for it or symmetric for it. So what you need to do is pre-distribute that key. You need to get that key to Bob or Amazon in advance. And that's the key distribution problem. You have to do it securely, and you have to make sure nobody finds out that key, because if somebody finds out the key, everybody using that key is potentially compromised. So if you work in a larger organization or been in an environment where you've got a notice due to a missing laptop or some other event, please update your key or access to the wireless network using the following. So a couple of issues, but private key is very computationally efficient, it's very fast, and that's why we use it today. So let's just take a quick look at public key and then how these things can apply to the Internet of Things. So there's really two types of public key methods out there. One called RSA, which many of you may have heard of. It was a very large company, now owned by EMC, and one of the two standards invented in the 70s by three professors at MIT, Rivest, Shamir, and Edelman, RSA. And in their public key method, it's very simple. Remember, everybody can see everybody's public key. So in this case, Alice takes Bob's public key and encrypts a message using the RSA algorithm. And she can now send that message to Bob, because only Bob's private key, which is mathematically connected and a little beyond today's discussion to get into, can unencrypt it or decipher it. So everybody on the Internet can receive the encrypted message, but only the person possessing Bob's private key, hopefully Bob in this case, can decrypt it. Very, very simple. So now I have a means of communicating over a public airway like the Internet and sending an encrypted message to someone and not worrying about it. One other method that I want to talk about, because we'll also look at it, is called the Diffie-Hellman method, DH or Diffie-Hellman, and it works somewhat similarly. And in this case, Alice has Bob's public key, because again, everybody can have access to everybody's public key. And using her private key, she computes a shared secret. So Bob's public key, her private key, computes a shared secret. And Bob, knowing that he wants to communicate with Alice, gets her public key, as you see at the bottom of the slide, and combines it with his private key. and computes, again, using the same algorithm, a shared secret. Those two shared secrets will be the same. And again, lots published on the Diffie-Hellman method. We're not going to go into in practice how that works, but it's 40 plus years of mathematical proofs. So here's what it looks like simply in a graphical form. Alice and Bob meet. Alice has the number 16, Bob has the number 9. Those are computationally connected to their private keys, but nobody technically sees anything below that line. So all of us on the phone see the number 16 going across the internet to Bob. We all see the number 9 going across the internet to Alice. Once they receive them, they do the computation with their private key and get a value. And as you can see here, they've computed a value on each side that none of us know what it is, no correlation to the number 9 or 16, but now we have a shared secret. And that shared secret can be used as a seed to encrypt things and to do a variety of other security methods. So having done that, one last slide related to this area, and that is advancing. There we go. Sorry, folks. And that is, how do I really know when I meet somebody over the internet? When you get that email that says it's Citibank here, you can't see them. You know, once you've met somebody, you have a reasonable chance of authenticating who they are when you see them again, subject to how good your memory is. But on the internet, or when it's digital and a device meets a device, or when somebody meets you digitally, how do you prove their identity? So there's one more concept that should be introduced here, which is called a certificate authority, or a trusted third party. And all that means is before Alice sends Bob her public key, she goes to a trusted third party and asks them to validate that she's Alice and that the number 9 belongs to her. And basically they do this by signing. And this is a cryptographic function where they sign her public key, and that converts it into another value, and here represented by capital X ampersand. Unrelated, and we transmit that over the public airwaves. And anybody receiving it, including Bob, can use the certificate authority method to authenticate that that number 9 is in fact from Alice, or at least belongs to Alice. Because what we would now do is go back and do again our key exchange, because I know if Alice can prove she has the secret or private key that corresponds to this, I'm talking to Alice. And that's really, I think, everything we need in terms of understanding security, where we've mapped what sort of tools are available to secure the Internet of Things. So these primitives, or these elements that are used in cryptography, allow us to produce elements in security that some of you may have heard of. So we've already talked about private key or symmetric ciphers. You may also have heard of them as block ciphers or streaming ciphers that are used to encrypt data. When you send your order to Amazon, it is encrypted. It is encrypted using a block cipher. We just finished 2 examples of RSA and Diffie-Hellman, of a public key exchange in the case of Diffie-Hellman and a cipher in the case of RSA. So this gives us the ability for 2 things that have never met before to create an element of trust between them over a public airwave. And again, that public airwave we're using here is the Internet. It could be your Bluetooth. It could be your Wi-Fi. Again, any communication or transmission platform, many of which now, of course, lead back or are interconnected to the Internet, create these public forums where we need these capabilities. We talked briefly about a digital signature, which is a method that allows us to validate the data or the key, the element, a way of authenticating at least one part of an exchange. And I'm introducing one other term here, which is important to be aware of, and there are many more, by the way. So this is not meant to be exhaustive, as is our definition of the Internet of Things. But a hash function is a cryptographic function that proves that the message you're receiving has not been changed or altered. So think of a contract. If you receive electronically a contract to sign, how do you know that line 10 was not deleted or altered? If you receive a request for funds, how do you know the numbers were not changed or altered? What a hash function simply does is it takes a message and digests it down to a fixed length code. And that code will only have one value based on the input. So that contract will produce the number 1234 in a very simple example. But if somebody changed anything in the contract, when you ran it through the algorithm, the value might now be 3569. Only the exact input will give you that exact output. So this is a method to make sure that when you're communicating the information you're getting about a product, the credit card, the order, the contract, has not been altered electronically by somebody on the Internet or in a public means or what have you. And it has some other uses, and it's also known as MACs and under different names. But these are some of the critical security tools that are now available to us. So now that we have this foundation of the Internet of Things and the range of things, and now we have an understanding of general security tools, so let's look at securing the Internet of Things. But as it turns out, there are challenges, and as no shocker or spoiler alert, given the title of this presentation, there are some significant challenges in securing the IoT. And in particular, because the Internet of Things really represents a broad range of technology, most traffic lights, for example, in America, have an RF or a radio frequency connection point. They actually can connect to the Internet. So most intersections are arguably part of the Internet of Things. Your cars, many of you, if your car is only a few years old, maybe a little older, has a connection capability to the Internet. So there's a lot of different technologies, but there's a couple of things that are common even on the larger platforms. So some platforms have little or no power. If you're wearing a Fitbit, if you have a battery sensor in your work that you use, whether on a production floor, what have you, you may have very little power, or in the case of an RFID or passive NFC tag, no power. It actually collects its power from the reader or from its environment. Very, very small computing platforms. We're going to talk in a few minutes about some of these computing platforms, what they look like, even though they might be used in very large vehicles or appliances. Quite often there's a restriction in time. You don't have all day to use these security protocols. And in fact, one of the reasons why we use particular protocols, for example, on our wireless router is not to impede the progress of the data. In the early days, if you set up a wireless router, there were probably instructions to minimize the use of security because it was going to impact the throughput and experience. And in some cases, not only does it impact the experience, but in fact, you're limited either by regulations or simple physical aspects. A car passing through a tolling booth has about 50 to 60 milliseconds to connect, whether it be through EasyPass, SunPass, wherever you are in the country, and actually communicate with the tolling booth, authenticate itself, and perhaps provide some data. So again, the restrictions could be physical, it could be otherwise. And another large challenge, frankly, for the Internet of Things is there really is no common computing platform. The reality is because there are so many different things that when you look at the IoT, and this is going back to looking at the IoT, you realize that whether it's a thermostat, a video camera, a smartwatch, you know, what thing you're seeing here is they don't all have an operating system, which we all take for granted when we go on our laptops or PCs and connect to the internet. They might not even have power in the case of passive devices, and they might have limited connectivity. So unfortunately, this slide summarizes where we're left when trying to secure the IoT, which is the tools that have been developed, and really over the last 35, 40 years, which referring back to the public key platforms, simply have not kept up or simply have not been developed with the thought that there would be these small little devices, little computing platforms that we were going to wear on our bodies, put in our cars, our houses, or implant in other things. So I think what that then leads us to is, so what can we do? What does fit? What is being done today? So I actually took this next slide as sort of a final part of a technical discussion, and we're going to go back to a real-world use case, which I think will make it helpful to bring all of this together. But this is a public key method, looking at some public key methods on a small, very popular computing device called an ARM Cortex-M3. It's a processor running at 48 megahertz. And this is actually taken from a recent paper at NIST that was delivered just 2 weeks ago in Washington. 48 megahertz. That is the speed that this processor runs at, the number of clock cycles or instructions it can process in a second, 48 million. To put that in perspective, if you're looking at this on your laptop or PC, that's probably running at 1.2, 1.8, 2 gigahertz or faster. So 2 gigahertz would probably be 2,000, actually in the calculation here, 400 times faster than this platform. So already we have, going back to my earlier slide about computationally restricted spaces, this is considered a pretty powerful processing platform for the very small embedded devices in IoT. So just quickly to discuss the important aspects on the slide. On the left-hand side is the security level. When people talk about security, it's like the temperature in the room. You can turn it up and down. It is 70 degrees in the room. How strong is the security is usually measured in bits. So we say that this security is 128-bit security, which is considered secret or good by the U.S. government. And you can have 80-bit security. You can have 256-bit security. So that's just the level of security, and it's important always to look at what level of security that you're looking to attribute or use. There's a couple of algorithms listed here. These algorithms were actually implemented in software, so you can achieve better performance than what's here in hardware. And it's showing you the ROM, the read-only memory, and the RAM that's being used. So this is the space being used in the processor. But what I want to draw your attention to is the right-hand side, the speed. This is in milliseconds. So this is the speed to do one of those authentications, to do one of those key exchanges and compute a shared secret. So you can see here that there's one very lightweight solution that runs in 15 to 34 milliseconds, but ECC, which is a U.S. government standard currently in public key cryptography, which is elliptic curve cryptography, which was invented in roughly 1985, takes upwards of 8 to almost 900 milliseconds in certain implementations. Now, that's 0.8 of a second, pretty fast. But keep in mind that my example of a car going through a tolling booth only has 50 to 60 milliseconds, maybe 80 milliseconds top, to complete its entire transaction. So if this were the platform in a car going through a tolling booth, you'd have a physics issue. It can't compute fast enough. There are, by the way, and in full disclosure, ways of making all of these things go faster by putting them in what's called hardware implementations in chips and silicon. But the purpose of this slide is simply to show that as fast as these things look running in milliseconds, they're still relatively slow in creating a challenge for securing the Internet of Things. So I'd like to try and bring all of this together as an example of securing the Internet of Things where it isn't happening or maybe where it could be happening. And I'm going to introduce one more platform called a microcontroller. And again, many of you out there probably know what these are. I would suggest that these are building blocks of the Internet of Things, not to exclude things like FPGAs, field programmable arrays, which are also a very significant building block, ASICs, which are application-specific integrated circuits. So there's a range of stuff. But for today's discussion, and just to sort of take us through a real-world example next, I want to introduce what a microcontroller is. Here are 3 examples by 3 very, very good firms. And in essence, they're a small computer with a single IC or an integrated circuit inside. There's a processor core. As a matter of fact, the one on the left has an ARM Cortex core, as we were just looking at a minute ago, in it. There's memory, so you can store things, applications, data, etc. And there's programmable I/O. And they're being used to design embedded applications. And so microcontrollers help me to describe the example I now want to use sort of as a bringing everything we've discussed together today in this discussion or this presentation for a real-world example, your car. So microcontrollers are used in most of the cars we drive today. They've actually been used for many, many years, but they've gone from 4 or 5 to, in some cases, over 100 microcontrollers or computers on board your car in today's vehicles. Here's a quick snapshot of typically what it looks like. So there's 30 to 50 microcontrollers in a vehicle. And they can be involved in vehicle controls, which are often something called 16-bit microcontrollers. And again, the processing speed and capabilities have to do with things like their data buses or the addressable memory, and that's really what these parameters bits, 16-bit microcontrollers or 32-bit microcontrollers. So the powertrains in our vehicles are controlled by this. Driver information systems typically have 8-bit microcontrollers. And again, these things are used on your brakes, steering, airbags, wipers, climate control. You know, they're the things that are sending over the car's system how to control them. So we've got a lot of computers on a car. So let's take a look. What could go wrong if you have a lot of computers running on your car today? And what I'm bringing together here to highlight the need and the value of security for the Internet of Things is a recent news item some of you may have seen involving a 2014 Jeep Cherokee. And you can go online and see videos of this, etc. But basically, the hack. 2 developers decided that they would demonstrate the, let's say, the exposure that we all face every day, perhaps without realizing it. So what they did is they created a system where they could access the car via the Sprint network. It turns out that all Chrysler vehicles, and this is specific to Chrysler, but Infiniti, Mercedes, BMW, as a matter of fact, there was a recent hack of BMW that we could have used as an example, all have these systems. So this is not meant to pick on Chrysler or anybody who's going home in a Jeep today, but they managed to connect to Uconnect, which is the in-vehicle communication system, which resides in the head unit. So typically, many of us have a screen or monitor in the center of our dashboards now, and behind that are the brains for a lot of our vehicle's activities. In the brains was an FPGA or microcontroller, and they were able to actually rewrite the code in the processor of that microcontroller in the head unit. And once they rewrote the code, it gave them access to what's called the Controller Area Network, the CAN. So this is the network that controls the car. For those of you involved in protecting your businesses on the Internet, you've put up all sorts of barriers and shields to detect intrusions into the network, to make sure people can't get at your data and other things. This is the network that connects all the different pieces of the car together. And by the way, they estimated that there was probably 471,000 vehicles vulnerable to this attack. And basically, once they sign on, they would get the GPS location of a car. They could see a car in Texas on a road. They would see a car in the Pennsylvania Turnpike. They would get the VIN number, a bunch of other data, the make and model. Maybe it was a Dodge Charger, in this case a Jeep. So what could you do? Well, if you watch the video, they start off by turning their radio up really, really loud while the person is driving on a freeway, I believe in Texas. They turn on the climate control system. They actually turned on the windshield wipers on a sunny day and started actually spraying the washers to the point where the person has trouble seeing. More important and dangerously, they could actually apply the brakes or acceleration and actually disengage the engine at one point in the demonstration. They also displayed a picture of themselves on the center unit in the car.
Oh my God.
And more. As a matter of fact, here was an example where they took control of a car that was parked and drove it into the ditch. So these are all the things that, this is a real-world example of small devices which are going into implanted into a lot of different places. But when you think about why do we want security or what's important, it's probably because other things are being hacked too, mostly for demonstration purposes to the world, and we don't really think about them. But web cameras, which serve some great purposes and what have you, are highly vulnerable these days. For fun, I'm not going to say for profit or necessarily to endanger any of us, refrigerators, medical devices. And recently the FDA has issued a warning about implantable medical devices because the way you adjust typically or control an implanted medical device is through RF, radio frequency. So the good news is if you watch Homeland, or you saw Dick Cheney on 60 Minutes a year and a half ago, you really can't be across the world and adjust somebody's pacemaker or defibrillator. But the basic foundation of the technologies to access a device and turn the medical delivery system up or down exist. Printers are quite popular, and there's actually was an interesting video from Columbia University where somebody went to an interview, said they forgot to print their resume. Could the person please print it for them? And when they opened up the object to print it, what they didn't realize is they planted a seed in the printer which gave access to the entire network of that corporation. And then through the printer, from the outside system, the hackers were able to achieve access to their phone systems, to their networks, et cetera, et cetera. So printer hacks may, again, the impact of what these things are when you see them on top. Light bulbs, we've all heard about light bulbs on the internet. Well, maybe we all haven't, but guess what? People have thought it would be really great if you can control your lights from your smartphone. And how do you do that? You give a digital identity to your light bulb and you put it on the internet. And people have hacked those, and there has been suggestion that some dangerous things could come of that. Thermostats, whether it's Nest, which happens to be a fairly secure platform, or some other thermostats that are less secure, which, by the way, many include motion detectors, which enable somebody to see where in your house you are, meant to give data as to when to turn the temperature up or down, but maybe that's not all people want to do with the data. And even door locks. You're probably already reading that Home Depot can sell you a door lock that if you're in Philadelphia and somebody has showed up at your home in Chicago, you could open the door for them over the internet because your door has a digital identity on the internet. So certainly the idea that we're getting convenience, we're getting performance, we're getting great things out of the Internet of Things is there, and also the potential exposure. So not that it's all that nobody should sleep tonight. People are working on this, or some people should be. And for those of you who want to continue following this topic after, and this again is just meant to be an introduction as to what are the challenges and possibly opportunities if you work for an organization who can solve this, and certainly there are many who work alongside us in doing this. ISO, the International Standards Organization, has several standards bodies who are working on cryptographic methods, protocols, and solutions for securing. These are just two that we're involved in, one of which we've actually submitted a standard for authentication and protecting data of these very, very small devices. The Industrial Internet Consortium, which includes some pretty large industrial folks in our country. All Seen Alliance, again, includes several large Asian manufacturers and local. Thread Group, another group focused on promoting standards for the Internet of Things, Open Interconnect Consortium, and IEEE, which is a great organization, and it actually has a subgroup on the Internet of Things called P2413. So people are working on this. There are some solutions emerging. Not all the devices that I've talked about today are as insecure as you might deduce from the car example. But again, the impacts on these things, the impacts on you should never be discounted just because it's a thermostat or just because it's the meter on your house for electricity. These things all connect going up and down the network and need to be thought of. So, in summary, and what we really talked about and gone over in the last 45 minutes or so is that securing small things is a challenge. And even things that are big, like a car, you look at it and you go, wow, it's got power, it's got this and that. When you realize that underneath the covers, it comes back down to small things again, and it's a challenge again. So looking for a solution can be difficult because then you start asking, well, what does my refrigerator, a thermostat, and my car have in common? Probably the need for security, but not much else. So again, securing these different things creates a bigger challenge. It's going to require some foundational protocols and methods. They can fit across the board. I did not include in my presentation today to keep us sort of focused, but if you think of everything on the internet as a continuum starting at the very high end, supercomputers, computers, PCs, pretty good security up there. And whether it's network security, we all safely can go to Amazon still after this presentation and buy things, or go bank or go on eBay, because a combination of public and private key methods together are authenticating you and then protecting your data. And it works on tablets, it works on smartphones. But once we start going down to smaller and smaller devices, implantable medical devices, the thermostats, the microcontrollers, the FPGAs that are making up the Internet of Things, it gets harder and a bigger challenge. So if you are working in the area, or if you are needing to use something that is going to become or provide something that is going to become part of the Internet of Things, you should think about what you really need to be doing. For example, authentication is all you may really need. You just want to make sure it's Citibank. There's no reason to protect the information afterwards because all they're doing is making an offer to come to an open house. No need to encrypt the data. Confidentiality? Maybe you do need to encrypt the data because now I'm sending you my bank statement. Integrity. Maybe you always need integrity because you don't want the information to be changed. You don't want to send people, a fun hack could be to simply change the date on the invitation of an email and send everybody somewhere on the wrong date or perhaps to the wrong location. So again, you may not need to encrypt that data, but you want to maybe ensure the integrity of it. So you should understand when you're creating devices and applications and solutions what you really need when you say, well, we need security or we need to provide security to our users so they'll adopt our solutions, our methods, or technologies. And the final thing I want to say is that, as I gave an example, a lot of the security that we use today is 30, 40, or more years old, and it works fine because our computers run at gigahertz speed. But the reality is a lot of what is building the Internet of Things today do not run at that speed, do not have that computing capacity, do not have that capability. So when you are looking for solutions to secure your devices or to use it, you may need to be a little more progressive and a little more open, which is in pretty much straight contradiction to the security community who wants to use only the oldest, longest existing protocols out there and doesn't consider anything else suitable, or you're putting yourself at risk. But the reality is those things don't fit. So you will need to, in some cases, make a decision. Do I use security as being defined in some of these standards groups now and being vetted, or do I go without? And because sometimes it comes down to that when you look at the performance, strength, and time versus the platform that you're trying to put these solutions on. So there are solutions, and as I've said in this presentation, what I've tried to do through a simple definition of the Internet of Things, explain the security tools that are available that have been developed, recognizing that not all of them will fit or work. An example of what happens when you don't perhaps implement security where and when you should. And by the way, most of the hack on that Jeep Chrysler is now being addressed through a update or a fix to the system by Chrysler. And unfortunately, oftentimes these things come as much from human neglect or human failure to implement correctly as they do from actually a technological flaw. So we've looked at what it is. And finally, in summary, people are working on this. If you've listened to this presentation because you have an interest of a device you're using, you are using a device and want to know what can be done to protect it, or thinking about doing something in the field, there is places to go and opportunities to become involved.
Great. Thank you so much, Louis. And during the next couple minutes, if you think of a question, feel free to submit it to AIM via the chat option. And we'll go ahead and start with the first question. All right. Somebody asked Louis, does AE work with an MO processor?
So I think what they're asking, so the ARM Cortex is a family of processors. M0, M3. M0 is one of the smaller, more constrained environments. M3 is somewhat larger. I used it as an example. There's M9. There's a range of processors. So M0 is one of the smaller ones, and yes, it has been implemented on an M0 processor. So it fits in a very small place.
Great. The next question is, can you give examples for industrial applications?
You know, when somebody says industrial applications, the first thing that comes to mind for me is things like the smart grid, and whether it's, you know, buildings and what have you connecting to our electric system, or even within a building or a manufacturing plant, machinery and operations being controlled in something called machine-to-machine. So here you have not even humans, you know, where you're interacting as the front end to a device, but rather it's two machines, and one machine's telling another machine to shut itself down or open up the valve or turn up the juice or what have you. You know, the danger there is always that the command is not coming from the authentic element, but rather from, again, for purposes of today, we'll call it a hacker or a rogue. So the reality is, you know, you may not, you know, want to know that the next blackout of our system could be because somebody instructed the electrical substation in your area to shut down, and not your utility company.
Sure, yeah, they expanded a little bit and said for warehousing, distribution, manufacturing, something, let's see, instead of consumer products.
Yeah, I mean, well, manufacturing, warehousing, what have you, an example might be traditionally we've put barcodes on objects as a way to identify them, and whether it's in clothing stores or a food store, what have you. And it's worked pretty good. Recently, 2D barcodes, or those QR codes people may become familiar with, can provide more information. And then the next level that we're now seeing, particularly in clothing and working its way up, is where chips, typically RFID, although NFC chips also are being put in driver's licenses, but for the purpose of this question, are being applied to garments, are being applied to high-value assets, things that are moving through a supply chain or in a warehouse, and being used to identify them and actually collect information on them. So in the case where you're dealing with either counterfeit goods or need to make sure you have a secure supply chain, you know, you'll want to just because you've put a chip on it that identifies it doesn't mean it's secure. Those chips are easily copied and cloned. So typically you want to add a security element to those chips also, assuming that you require that capability.
Great. Okay. This question coming in from one of our participants. They say, it seems to me that the challenges outweigh the opportunities at this point with all of these devices connecting to each other, to the internet, and data being collected at such a high rate. Kind of like the Wild West at this point. What are manufacturers like Jeep doing to secure things? Do they have folks that will work with the emerging standards groups that you mentioned, or are they just kind of waiting for someone to create a solution or force them to follow the standard?
So it's hard to answer across the board. So traditionally, it's always been what's the shiny new thing. So when it was Wi-Fi and our wireless routers, nobody really thought about security when they first came out. Many of us installed our first Wi-Fi systems with no security. And then, so you heard of 802.11, which is actually a committee. It's a standard, but it's a committee. So we all had 802.11 routers, and then we got 802.11a and B and G and now N and higher. And what's happening is in each evolution of that standard, they're trying to fix the security issue because they issued it before they had addressed it. DVDs, the same thing. So it's sort of our traditional way of rushing out a new technology. It's all shiny and new. It works great, and then worry or be confronted with the security issue after the fact. So unfortunately, in some cases, it's nothing new here. Specifically to the automotive sector, there is security in some areas, and not all of the devices are quite as open. And by the way, this was not an easy process. This was not somebody, sitting at a Starbucks for a few days coming up with these hacks. I mean, these people downloaded engineering manuals, actually took 2 vehicles under a grant and dismantled portions of them to figure it out. But the point is, it could be figured out. So the people who are providing these building blocks, the semiconductor companies, microcontroller FPGA companies, they are working to incorporate security into their products. So when they can provide them to the automotive businesses, they'll have these foundational building blocks with security that they can then implement. As I said, Chrysler is already doing a firmware update. Unfortunately, you have to take your vehicle into the dealership to do it. They can hack you wirelessly, but to fix it, you need to go in. But there is a fix, at least for part of the hack that I described in today's call. So people are trying to address it. You also have to keep in mind that there's like a 3 to 5 year development cycle in a lot of this technology and parts in the automotive sector. So unfortunately, some things identified this year or last year, you may not see till your 2019 model. So drive with caution.
All right. I also sent this one to you, and I'll read it out loud just to make sure that I get it correct, but from another participant. What do you think about Ucode DNA, which uses ISO IEC 2916710 standardized cryptographic security, 128-bit key based on AES?
Okay. So first, let me explain the question, and then I'll give you an answer. So somebody's asking about a particular chip that has recently come out. It's an ISO standard, and that chip, it's specifically RFID. Or actually, although the standard applies to near-field communications, to a range of RF technologies in the 18,000-X suite. But basically what somebody has done, which is really, really quite wonderful, on a 1 megahertz, so 2,000 times slower, smaller, virtually no resource platform, no power, has put a cryptographic engine called AES, which is a private key. So we all remember private key means we both have to have the same key method on this chip. So it will run and talk to a reader or somebody trying to communicate it at 128-bit security level. So that we also looked at what security levels are, and 128-bit security level is a very good security level. So I think it's great that they did this. I think it's going to have a lot of use in a lot of different areas. It doesn't answer everything that's needed because, again, keep in mind this is one of those secret or private key systems. So when that chip shows up, you need to know the code on it, the secret, so you can, in fact, communicate securely. And the challenge is if you're putting those chips, again, in, let's say, smartphones that are getting distributed by the hundreds of millions anywhere in the world, you now need to get the secret key that belongs to that smartphone wherever somebody's going to need to use it or want it. So there are going to be challenges. But it's a great thing that has happened, that somebody has demonstrated that you can put security on these small chips. And this is one of the smallest life forms, much smaller than a microcontroller, that we were just using as an example during my presentation. So hopefully that answers the question.
Great, and we have a couple more questions. One is, are there things that the average consumer can do to better protect themselves? What's best or easiest?
What's best or easiest? So, first of all, one should probably understand whatever device it is you've purchased, whether it's a thermostat or a washing machine or what have you. What exactly it's doing. So, for example, if you own a Nest, you should know that it's collecting data about your usage, your location, and what have you, and putting it up into a large cloud database, as is the smoke detector. And they're using that data, for a variety of things. So, nothing specific to you per se, but you should know that that data is being aggregated as part of the 25-page thing you just clicked, I accept, like we all do with our smartphones or what have you. You should understand where, you could as a consumer understand where that data is, who has it, or who's going to use it. So, for example, if you stop using your Nest smoke detector or carbon monoxide detector, they keep your data. You actually have to physically contact them and ask them to remove your data from the database. Now, this is a pretty innocent example, but there may be other things where they're collecting more specific data about you using a device you've purchased. So I would just suggest you understand what it's connecting to. We all download an app, and you always wonder, gee, if I downloaded that flashlight app, why does it want to hook up with my contacts on my smartphone? And oftentimes there's more than just that function going on the phone, and oftentimes not. So understand, what's connecting and where the data is going and what it's being used for is probably the best somebody can do at this point in time.
Great. Another question. You mentioned standards groups that are emerging to help, quote, tame this new territory and help provide solutions. But will manufacturers and software makers be legally bound to these standards, or will the government adopt these standards as protocol?
That's a great question, and I can tell you what the rumblings are, but I can't tell you what the end story is. So the rumblings are the government's very focused on this. If you go online, you can actually get a document that talks about securing medical devices published by the government. Very focused on what's happening. The FDA is issuing warnings about hacking of medical devices, etc. Several, I want to say congressmen, have issued a document calling for legislation on securing vehicles, especially in light of the hack that I just described. So they're calling for legislation that will force certain disclosures and certain protections for people buying a vehicle now that they see what's going on. So there are things happening, but unfortunately I can't tell you where they'll end up because we all live in the same system, and the same system says that there are other people in Washington not elected whose purpose is to influence what happens. And it'll be a subject of their agenda in the end, unfortunately, which I would not, suggest anybody they not get involved or push for what's needed. But where it'll end up is hard to say.
Yeah. Thank you, Louis, for your insight and knowledge into the Internet of Things and providing us with this presentation today. Thank you to our audience for their active participation. I hope that you all found this information to be valuable. We would like and appreciate your feedback, so please take the time to complete a brief session evaluation, which will be sent to you all shortly. This information will be used to develop future presentations in our AIM webinar series and future AIM Inc. events. Thank you so much and have a great day.